right? I mean, this is not a trivial classification algorithm like you saw previously, right? I mean, in trees it was pretty simple to interpret and stuff like that. But this topic, support vector machine, has a long history. Okay, so this was in around 1960s. Vapnik, he was a Russian mathematician who was working with some of these early ideas on classification, and this idea was, this stayed dormant for nearly 30 years until it was revived back with one of his colleagues. There is a beautiful history behind this support vector machines. I think that's available in YouTube. I can share the link with you later. But this is not a very the beauty about support vector machines is that it is also it's a natural, classification algorithm, but at the same time it's highly non-trivial on why this works in other higher dimensional spaces. Okay, so these are the two contrasting things about support vector machine, right? I mean, when there are two classes, the immediate thing would be to just draw a line and then say that, hey, this line separates these two classes, right? But on the other hand, to see why they really work and what happens if we have some complicated data sets, right? I mean, when it is not linearly separable, we will go over that to say why, how we will be able to do the classification, right? There is an inherent mathematical structure to it. There is an inherent mathematical beauty to why support vector machines work. Okay, so those things that we would be seeing over today. So it's slightly mathematically sophisticated topic. Okay, so it's non-trivial. That's why it's always best to read these things before you come to the class, right? I mean, it's always best to go over some of these things, and then so that you will have a much more informed appreciation for what we are going to talk now. So that's the agenda for today. First, we will go over what we mean by linear discrimination, and we will go over non-linear discrimination, and we will see what exactly SVMs are mathematically. Okay, and then we will see some of the extensions as well as drug design and kernel functions. How many of you have heard about support vector machines here? SVMs? No one? Oh, okay, okay. So basically, this is a classification system. This is based on what is known as convex optimization. Okay, so convex optimization is one of the very fundamental problems, mathematical problems, and mathematical modeling. When we have some of the constraints that are imposed, and we have to solve a bunch of equations, and if the set under in which the constraints could be solved is convex, it's the problems reduces much more easier. Okay, so that's the general idea behind the convex optimization, and support vector machines, or essentially the classification system, is based on convex optimization. Okay, and and these are known as kernel methods. Support vector machine is a part of what is known as kernel methods, and it is, I mean, we can derive lots of insights when we can formulate the original problem into a different problem. The way that some of these algorithms work, right? It's, usually in mathematics, when you see that there could be a small problem, but when you cast it in a different problem, the problem which is cast could be much easily solvable. Although, that kind of a transition is what makes some of the really beautiful algorithms out there. Okay, so there are different ways of looking at the same problem, and when you cast the classification problem into a different problem, which is based on convex optimization, it becomes much simpler. So that's the idea behind convex optimization. We will go over that. So the fundamental idea is the dot product, right? The dot product is a measure of similarity. Okay, so when you have two vectors, A and B, what is the dot product of two vectors? A, B cosine theta, right? And if the vectors are orthogonal, the dot product is 0, right? So it measures a similarity when the two lines coincide. you have the dot product as 0, right? So that kind of measures the sense of similarity, right? So that's the idea behind these optimization with the support vector machine. So for instance, you have a bunch of points here, the red points, the red dots, right? And you have a bunch of blue dots here, right? Now how do you separate them? What's a natural way to separate these two data points? Just draw a line, right? It's as simple as that, right? So this is what support vector machines are ultimately, right? If it's as simple as that, you naturally draw it, and so you can say that let's say these points are classified as xi's and yi's. This is in general is f of xi is greater than 0, you can say yi as 1, and these two classification. If it is 1, it's red. If it is -1, it's blue. So it maps a function, right? So this is a decision function for a binary classification. Okay, so this line is a decision function, right? So the support vector machines they pick the best separating hyperplane. Okay, so all support vector machines do is they just draw a line here, okay, between these two classifications. Now, how do we draw the line? That is the whole question that we are going to answer. Okay, so the training process is an optimization process. We need to pick the best line that separates these two cluster of points, right? And the training set is effectively reduced to a relatively small number of support vectors. So that's right, you don't have to work with all the points, right? So for instance, here, right, to work on these, to find this point, you really need you don't have to know information about these 2 points, right? All you need to know all the points that are near this line, right, to draw this. This vector is not going to change if these internal points change, right? So there is an information that the information recedes as you go away from the boundary. So you don't need to use all the information to construct this line, right? So that's the idea. That's the center. That's the critical idea behind this. Okay. So what happens if you have more features, right? We may say, we can do it for, this is just for 2 dimensions. You can have the same idea in 3 dimensions. So what will be a line in that case? We have a 2-dimensional plane, right? So yeah, and these are called hyperplanes, right? So what we need to the idea is if you have the data in 2 dimensions, we can actually, if the data may not be really closer in 2 dimensions, I mean the data could be crazy in 2 dimensions, but we may project that into higher dimensions and draw a plane. Okay, so these are called as kernel tricks. Okay, when you hear the word kernel trick in the context of support vector machine, you have to think that the data is somehow mapped into higher dimensions. Okay, so that's the idea behind that. So what are kernels? It's mathematically, kernels are nothing but transformations, right? Those are just nothing but you know about linear transformations, right? You have a matrix. Matrix is a linear transformation. So in general, you can think of kernels as a matrix. It's just a matrix. In when you have the continuous version of it, you have the integral and blah blah blah. But forget all that. But when you don't have, when you have the data is discrete, you will have it's a matrix. Those are the kernel functions. What they do is they take 2 points, right, and then they map. They give another point, right? This is a mapping, right? So in support vector machines, the key idea is to maintain the kernel, the inner product between these two, or the dot product. Okay, so I'm just giving you an overview of it. We can go into much more detail and then see what these means. There are examples of kernels that you can have. There is a linear kernel, which is a dot product, or you can have some polynomial, or you can have some other crazy function. Okay, so you all know about perceptron. Did you read about perceptron? I think that was your previous lecture, right? No? Okay. Perceptrons are a basic type of networks, or it's a very primitive version of neural networks. I think the next lecture is about neural networks, right? So these are perceptron is some basic, but so what you can think of it is, you can think of a binary classification, right? This is a line, right? So you can think of this in terms of equation. What it means is that this line is W transpose X plus B equal to 0, right? And all the points that lie outside of on the red dots, right? It is greater than 0 and this is less than 0, right? So that is the separating hyperspace, hyperplane, right? You can think of it as, all these points, right? You have to you can when you have this, if you have this line given by this equation, then all the points about will be greater than 0 and all this will be less than 0, right? And so this classification is nothing but a sign of this. If you have -1, it's going to be denoting all the points here. If it is going to be +1, it's going to be all the points here. So if you take a point and then evaluate its sign, you can say which decision space that it falls into, right? You can fall into the space on this red on this space, or in this space. You can figure that out, right? But which is a linear optimal separation? So you have a tumor. Let's say that you have a bunch of tumor and you have a bunch of normal here. You can have this line, right? Or you can have another line here, right? Like this. Or you can have another line here, right? So what is an optimal line here? What is an optimal line that separates these two clusters? How do you go about in finding that? What's that? Biggest margin. Okay, what do you mean by that? Right. What's the closest point to the line? Just this point? Let's say that, is this just this point or this point? How do you define that? How do you define the closest point for a bunch of points? Yeah. Use the what? But remember also another thing that I was telling you, that only these points matter and these points really doesn't matter, right? The internal points, let's say, does it really matter? No. So what is a natural thing to do to find the nearest point? Distance between which and which point? The green and black. Do you find all the distances? Closest? What do you mean by closest? Okay. The idea is to just draw a convex hull. Okay. So a convex hull is nothing but the convex set defined by the point, so that all the points lie inside it, right? So you draw a convex hull. Okay. So convex, this is when you have a bunch of points, right? You draw a convex hull, and the closest point, you can find the closest point in the convex hull that separates these 2 points, right? So that's the idea, right? You draw these convex hulls, right? And you can draw a perpendicular to this line, right? And then you can see what is W. It's going to be D minus C, right? D is the distance, this distance, and this is a vector that is perpendicular to that line, right? You take the closest point in the convex hull, not in the cluster. Okay, so that's how you resolve all ambiguities, right? So you can always define a closest point in that hull which lies closest to this line, right? And then you draw the perpendicular. Now to do that, right, we can see that the distance from the example data to the separator, you can draw you can derive this equation. It's going to be W transpose X plus B by the norm of W. You know the symbol norm? This is the absolute value. If you have 1 point, it's absolute value. If you have 2, right, that's the mean square root of x1 square plus x2 square, right? It's the distance, right? That's the norm is a metric. It's a distance, right? So the data closest to the hyperplane are support vectors. Those data points that are closest are support vectors because they provide the maximum support to the hyperplane, right? The decision boundary, right? The margin rho of the separator is the width, right? So that's the width of the separator, right? So you can find these two points here, right? And you can see that the margin, you want to maximize the margin, right? So that's the whole idea, right? So maximizing the margin, right? Which means that only the support vectors are important, other data are ignorable. You don't have to be concerned too much about the other points, right? But it also means that you are minimizing the complexity, right? And essentially, it only depends on few points and not all other points. Like for instance, you can draw a skinny margin, right? But this is more flexible. You can change it here and there. But this is more complex. But instead, if you have a fat margin, right, this is less complex. This is, you can't really change much in this. The degrees of so that's the idea, right? Assuming all data points is at a distance larger than 1 from the hyperplane, you can pose this problem of finding into two equations. One is W transpose xi plus b is greater than or equal to 1, and W transpose xi plus b is less than or equal to minus 1. Okay. So for support vectors, this inequality becomes an equality exactly at that point, right? These two equations becomes exactly same, and so you can write the distance of separation r is W transpose x plus b by norm of W, and the margin is 2 over the norm of W. Okay, so you can derive these equations. It's pretty simple. Okay, now so that we can formulate the whole idea this like this. You have to find a vector W and B so that the rho is 2 over norm W is maximized, right? Constraint, with respect to the constraint, W transpose xi plus b is greater than or equal to 1 if yi is equal to 1, and this is less than or equal to 1 if yi is minus 1. Okay, so you can write all this into this bunch of mathematical problem. Okay, now there is a corresponding quadratic optimization problem that has been solved in the early 19th century. Okay, so Laplace um, uh, uh, formulated this problem. I think it was Laplace or Legendre. I forgot. But the problem was this: you have to find a vector W and B such that this quadratic function half of W transpose W is minimized for all these values. Okay, so with this constraint, so this is a corresponding optimization problem, and to solve this problem, you just need to solve the corresponding optimization problem. Okay, so that connection that you can make is what actually drives science in general, right? You find two disparate ideas and then you try to see how they can be mapped and try to reconcile those ideas into a framework that you can solve. So that's exactly what's happening here. So once you formulate this problem mathematically, you see that there is already a problem that has been formulated and you try to solve this problem, right? So we need to optimize this quadratic problem subject to some linear constraints. So it's a classic linear optimization problem. Okay, so this people had been studying forever. I mean, so there are classic solutions for it. So you don't need to be really working hard on it. It was not Laplace and Legendre, it's Lagrangian multipliers. I'm sorry. So this is a class of problems that's already been known, and this is done by what are known as Lagrangian multipliers. Okay, this is a classic technique in calculus for solving some of these problems. This comes, I think, also in physics when you have a beads and I think it is a Brachistochrone problem. Like when you what's the shortest path that that a bead can travel from a point A to B, right? So when you do see these types of problem, you come across these kinds of optimization where you solve using Lagrangian multipliers. And there is a solution for it. All you need to do is find these alphas, right? So that this quantity is maximized to that constraint alpha of yi equal to 0. So that's what we need to do. And there is already an existing solution of the form. It is given by w equals summation of this quantity here and b. So there is an analytic solution. You don't have to slog through a tree-based methods in which we don't know how the tree is going to be constructed. And here you have a perfect analytical solution to the problem. So all you need to do is code this, right? And then you can have your support vector machine. And so once you have this, you can evaluate it, right? At any point x, you can evaluate this function, and then you see in which part of the plane it lies in, right? It lies above the line, or I mean in either sides of the line. You can just evaluate this function, right? So this relies on the inner product between the test point and the support vectors. Okay, so we will see that, and also we have to take an inner product between to solve this, right? If you look at this here, it is an inner product that you have to solve between all pair of points. Okay, so if you are having n points, what's the complexity for this? When you're trying to multiply two vectors of length n squared, right? So it's a very complicated problem in terms of computational time, but there is a neat way to do it. We will see that. Okay, so what if the training set is not separable? Okay, let's say that there is some point here that falls in here, right? So in that case, what we will do is that we add some slack variables, and then we can solve this optimization problem, a corresponding optimization problem. So all we need to do is find w and b such that the c times you impose a constraint c, summations, the slack variables are minimized. Okay, so what is that? Do you recall something similar to this, what we did? Regression, ridge regression. Yeah. Yeah, exactly. That's because when you take the norm, right? I mean, there's a square root function. Yeah. So yes, actually, it's because of some mathematics that goes into quadratic optimization. It's for normality purposes, right? I mean, when you out a scale, and that makes your problem much easier to formulate. So that's a convenience factor, but it doesn't matter in the solution. You can take it a half or not. Okay. Now that parameter c can be viewed as a way to control overfitting. Okay, so this is exactly the kind of thing that we did in what? Ridge regression and lasso, right? So that you see a similar pattern here for overfitting when you have a soft margin, right? So for soft margin classification, you can describe again a dual problem, right? And you can use the dual problem, and then you can solve this problem. But then remember this, for this you need to compute w and b, right? But at the end of the day, we are interested in classification. So you really do not need to compute w and b to find whether a point lies on which side of your splitting hyperplane. You really don't need to compute these quantities w and b, because at the end of the day, we are only interested in f of x. We are not interested in w or b. Okay, so got this point here? You understand? Actually, there is a typo here. There is a b here. But look at this. To solve this problem, right? You may be thinking that we need to know b, w and b, right? But it's not necessary. Why? Why it's not necessary to know w and b? Because once you know alphas, right? Here, once you know alphas, all you are interested in f of x. What is f of x? It tells you whether it's -1 or 1, right? Whether your decision is, you are going to make a decision saying that this point belong to that side or this side, right? So all you need to compute is f of x, right? All you need to compute is this quantity, right? So you really don't need to know w and b, okay? So, and there is also a theoretical justification for all this. I don't want to go into this, but the point is that the complexity of the classifier is really, really small. That is one of the biggest strength of linear SVMs, right? So the classifier is a separating hyperplane. It's just a line in 2 dimensions, a plane in 3 dimensions, etc., etc. And the most important training points or support vectors, they define the hyperplane, okay? And quadratic optimization algorithms can identify that points, non-zero Lagrangian multipliers, right? And both in dual formulation of the problem and in solution training, right? So all you need to do is this compute this quantity, xi transpose x, right? So that's going to be solved for you. In terms of nonlinear SVMs, okay, so this is fine. We are in a perfect world. We see that, okay, here are some points and here are some points. Draw a line and classify these. But what happens? Let's say that you have these two. You have a line, right? And there are some points here, and there are some points here. Now you can say that, oh, these points belong here and these points belong here. Now, what we are going to do if the data set is too hard, let's say, for instance, there are some red dots here, there are some red dots here, and in between there are blue dots here. How do you go about doing that? The thing is this: when you project this is a 1 dimension, right? When you can project this to 2 dimensions. So for instance here, what I'm taking is, I'm taking this data into 2 dimensions, right? When you take the data into higher dimensions, you see that there is a plane that separates these two, or here a line that separates these two. So, you can solve the problem, right? So by taking the data into a higher dimension, you can clearly solve the problem which you may not be able to solve in lower dimensions, okay? So that is one of the biggest strength of SVMs, okay? So how to go about in doing that, right? So the idea is this: to do that, right? When you, let's say that a data might be, if you are projecting all this, let's say that if you are projecting these in 1 dimensions, what's going to be there? There's going to be such a set of black dots, and there's going to be blue dots, and here there is going to be blue dots, right? But if you make it, you can draw a circle, and then you can classify, and then say that, okay, so this is all going to be the classification plane. But the idea is, for nonlinear classification, you need to define the inner product or the dot product, okay? So just like how you have dot product in the dimension, when you project the data into a higher dimension, you need to have a circle here. Instead of a plane, you need to have a circle, right? That separates, right? In the previously, it's just a line, or here it's just a point. Now you're taking into 2 dimensions, it's a line here, right? But if you take it to higher dimensions, the classification boundary may not really be a linear model. It may not really be a line or a hyperplane. It could be a circle, or it could be any other crazy shape, right? And that transformation, right, to make it into a circle, or what kind of a curve that separates these 2 points, right, that is made by what is known as a kernel trick, okay? So to do that, all you need to do is take the dot product. There are several dot products. You need to make a transformation. You need to make a transformation for the point x to phi of x, so that these two can be separated in higher dimensions. Okay, this is what is known as a kernel trick for SVMs. For nonlinear SVMs, you can do a kernel trick in which you can take the data, transform it, and in the transform space, you will be able to separate a linear and a nonlinear way, right? So that transformation, that kernel trick is facilitated by lots of kernels. Okay, there are several kernels that you could use. Okay, there are really classic kernels that people generally use for using support vector machines. So it is facilitated facilitated through the inner product. So in general, if you have a dot product, is one transformation. You have k of xi xj is given by xi transpose xj. Okay, so this is just a normal dot product. A normal dot product can be thought of as a transformation. Okay, but you can have some function phi that is also a dot product. That's you can have phi of xi transpose phi of xj. This is a dot product too, but this is a transformed generalized dot product. You can think of it as more generalized dot product. Okay, and that is the kernel function, depends on what function you can use. So for instance, right, in two-dimensional vectors, if you have x1 and x2, and if you define k of xi xj is 1 plus xi transpose xj squared, if this property is maintained, you can immediately apply the standard algorithms and then separate it. Okay, so this is the kernel trick. All the kernels that satisfy this property, k of xi xj is phi of xi transpose phi of xj, or kernels that can be used for support vector machine. So for instance, k of xi xj, you can see that it is same as phi of xi transpose phi of xj. Okay, so this kernel trick can be used, and there are lots of kernels that can be that can be constructed. So for instance, when you have matrices, talking in terms of matrices, I was telling you kernel is nothing but a matrix, right? A square matrix is called positive definite if x transpose ax is greater than 0 for all non-zero columns. Okay, and it is negative definite if you have this property. Okay, so the reason why I'm showing here is that there is a theorem that states that every semi-positive definite symmetric function is a kernel. So there are a bunch of kernels that you can define. Okay, and so once there are there are infinitely many number of kernels. So for instance, for linear kernels, is xi xj is given by xi transpose xj. If you have a polynomial, that the previous example that I showed you is an example for a this is an example for a polynomial kernel. Okay, and also there are something called Gaussian radial basis function kernels, and there are two-layer perceptrons, and there are so many kernels. Okay, so you can similarly formulate the same problem, right, in for these kernels. So all you need to do is, instead of xi and xj here, you need to do k of xi xj. Okay, so once you know the kernel, you can apply SVMs just like that for nonlinear separation. Questions? Guys need to be asking questions. Yes. Right. So any function that should satisfy this property, k of xi xj is given by phi of xi transpose phi of xj, is a kernel. Yes, there are infinitely many, but yeah, right. Right. There are some standard things that's one of the key problems in support vector machines, and depends on the data set, and it's a trial and error things that you need to pick and choose. But yeah, that is one of the biggest questions, right? Yeah, that's a key thing, right? So you try to separate using Gaussian kernels, but there are some, most of these problems in machine learning are also data dependent. Actually, that is where domain knowledge comes very important, right? And data science and things like that, right? I can't tell you that, oh, this is the best kernel that you can use, because some problem could be linearly separable, some problem may not be linearly separable. So for that you have to use some other kernels. But these were proposed originally by these guys in 1992, and they became very popular in 1990s, right? And they are doing really good for genomic data. Today there was a talk in microbiome by Johan, who was actually, he was using SVMs for taxon predictions in microbiome, for the throat, for the microbiome that exists in throat. So I mean, he was using machine learning to do that classification. And they have been extended to a number of tasks such as principal component analysis, etc., etc. And they use both. There are several picks and tree, things that you can use for using SVMs. Like, but then, right, tuning SVMs is a black art. Selecting the kernel, the parameters, it's usually done in a trial and error way, right? I mean, of course, you can use cross validation too with support vector machines, right? That's another thing that you can always do, right? When you don't have an analytic formula, you can use a, the testing error matters, right? And there are XVM extensions for regression problems, variable selection, etc., etc. So there is an example in drug design. The goal is to predict bioreactivity of molecules, and the target is to predict the logarithm of inhibition concentration. So there are labels on site A, and the training set is on 66 molecules. These are old data, but it was shown that SVM really did good. I mean, they were really good in solving this problem, right? And so for this problem, the training data consisted of 66 molecules with 323 original attributes. And the testing results, you see that the true value and the predicted value were almost linearly correlated. So yeah, so there are many other applications. For instance, it was used in handwriting recognition, speech recognition. I think the AT&T Bell Labs used it for handwriting recognition. Wapnick first, he vouched that this SVMs are going to beat other existing algorithms at that time for handwriting recognition, and it was proved to be really, really good. And speech recognition, etc., etc. It's used in several applications now. It's part of any standard package, okay? And this is where generalization theory and practice meet. That's one of the beautiful aspects of SVMs, right? The general methodology for many types of problems. You can have the same program and a new kernel, and you'll have a new method, right? And there's no problem with local minima. So most of these problems are hard because when you have non-convex shapes, the optimization problems becomes really crazy, right? So you don't have such problems with these. And there are few model parameters, and and there are very successful applications of it. Today we will just go over one of the very basic tutorial in gene expression data, okay? But there are several open questions for SVM. Will SVMs beat my best hand-tuned method? Don't know. You have to try. Do SVM scale to massive data sets? And how do you choose some of these parameters, right? How to handle categorical variables? How to incorporate domain knowledge, and how to interpret results? So these are very, very open questions. And there are lots of support vector machines tutorials out there. Our book is one of the best books for it. So yeah, with this, I will end this talk for support vector machines. I mean, the thing is that, it's more mathematical, and you have to appreciate these concepts by going a little bit deeper and trying to think about it for a while to understand how these things work, right? So it's very important that you spend time on reading and then thinking about why they work and stuff like that, right? And also, mathematics is like you have to write it down, okay? So nowadays nobody writes. I think that is one of the very unfortunate things. But math works only through practice, right? So you have to write those equations and see why they make sense. So but then if you read that, you will see that it's one of the very best algorithms, and there is a inherent math